Firstly, thank you very much. And let me actually point out as we're kicking off, this session will be recorded. So if you have interesting questions to post in the Q&A, please know that they're being recorded and hopefully that leads to some really fabulous responses from our attendees. If you do want to post questions at any stage, if you're new to Zoom webinars, just hop down to the Q&A section at the bottom and feel free to post questions at any time. We'll address as many of those as we can come the end of the session. So welcome to the UTS Data Science Institute Data Discovery Seminar Series. The Data Discovery Seminar Series is a program of talks exploring the intersection of data science, artificial intelligence, society, industry, and government. We'll hear from amazing speakers from across the intellectual spectrum, leaders of business, pioneering researchers, and the people impacted by the work we do at the forefront of data innovation. The UTS Data Science Institute is excited to host the Data Discovery Seminar Series, and it's a great fit for who we are as a team. We're a group of data scientists, data researchers with a focus on delivering impact and value through engagement with business and government. Our eyes are always on the real world value of the work we do, and that rhymes perfectly with the purpose and direction of the Discovery Series. Today's session is a perfect illustration of bringing the real world into the land of the digital, and then using that to drive actual, meaningful, and evidence-based decision-making. Digital twins allow us to see our amazing world in brand new ways, helping us better explore how our complex and often emergent systems interrelate and interact. To understand how those systems have behaved in the past, is behaving now, and might behave in the future, and providing a platform for you to zoom out to the macro or zoom in to glimpse the micro. Digital twins are a beautiful illustration of what can happen when IoT, data visualization, GIS, and smart algorithms come together to deliver practical tools for users across industry. And I really can't wait to hear more from our amazing panel of speakers today. And we're coming from around the world to you today, which is, I think, pretty exciting. Before commencing, I'd like to acknowledge the Gadigal people of the Eora Nation, upon whose ancestral lands our city campus now stands. I'd also like to pay respect to the elders past, present, and emerging, acknowledging them as the traditional custodians of knowledge for this land. As I mentioned at the start, before we kick off, please do be aware that we're recording this seminar and that a version of this may be posted online. So keep those questions fantastic. And if you manage to miss anything today, please do check our website for more details, and hopefully we'll have a copy of this session up soon. Now, thank you very much, everyone. This will be the end of me speaking until right at the end, because we've got far more interesting people to talk. So Simona, over to you for a formal introduction, and then we'll kick off.
Thank you, Adam. So let me just share my screen. Can you see my presentation slide? I hope all good. Yes. Before I start, I would like to say that the idea of this seminar actually came after the progress we had last year in 2021 around the digital twins, and after discovering that around the world there are fantastic researchers, academics that are tackling the same problems that we are trying to do with a different aspect. So today's seminar is all about providing you with an insight of a little bit what we're doing in Australia. I'll be taking just a few minutes just to introduce the work, but I will leave the stage to our collaborators at the University of Technologico from Monterrey, Mexico, to be able to share with us their work and their vision about what does it mean, a digital twin. So this is part of the UTS Data Science Institute, led by distinguished Professor Fang Chen, and the institute has been created in 2019 with the purpose to apply artificial intelligence and data science to solve some real world problem. As part of that, inside the institute, we, the Future Mobility Lab, are trying and focusing on applying data science to solve, in general, mobility and smart city related problems. So over the last years, we've been working across several areas, from public transport, from a normal traffic congestion prediction, up to any type of mode, electric vehicle, emergency of new on-demand, shared autonomous vehicles, and so on. There is a little bit of recognition from for what we are doing, and we are happy to let everyone know that last year we had 3 finalist awards for the work of the digital twin that I'm just gonna give a short demo of on the ITS Australia Awards and also on the IoT Awards. So we are pretty happy that we get recognition for this work, and hopefully we can extend even more outside of our borders and work with international researchers and academics to improve and learn more, and why not grow, of course, our knowledge. So what is the digital twin? For those of you that are watching this seminar and might hear it for the first time, we usually refer it as a visual representation of either an object, a system, or a real life system that basically is trying to solve some problems. Either we are talking about the virtual representation of a car, the virtual representation of a city, or the virtual representation of an entire production unit. All of these are part of the digital twin modeling. So it's basically the exact counterpart of a physical thing. Now, why should we use digital twins, and why people have started to talk so much about them? More and more, there is this need to create absolutely scenarios in a virtual environment where we can test hypotheses without changing the virtual system itself. We want to be able to visualize either products that are being in use or some operations that are happening in real time. And in order to be able to do that, we need to have this replica, this digital replica, where we can actually take actions in order to build a digital thread and connect different systems that might work individually. All in all, this whole digital representation, it's all about being able to make informed decisions and being able to change aspects of that system that do not work in order to improve it. So with regards to the impact of digital twin around the world, there are several industries that have already adopted. Either we're talking the automobile industry, the aerospace, even in healthcare. Smart cities are big adopters of digital twins, and you'll hear more and more about this, but not only the construction industry, in order to build like new virtual replicas of the buildings, of new spaces, and how these are being used by people. We're talking manufacturing and so on. So there is quite a lot of impact of the digital twin around several sectors. But if you actually think about it, it's all about an interaction between the physical system, the virtual system, and services that we can provide in between the two across the data that is being generated. So when it comes to digital twins, there is a layered approach that is being applied. One can start with the simply terrain, adding on the buildings, the infrastructure around those buildings, in order to be able to then add any mobility like vehicles moving or entities moving, pedestrians, and so on. And on top of that, we can add the digital layer and the data layer to finally get what we want. So this would be like this layered approach, but it's not that obvious and simple to get to. When it comes to maturity levels, according to the definition of Atkins, there are 5 maturity levels. And around the world, from what we have experienced, a lot of researchers are working at level 0, 1, and 2. What does that mean? It means that mostly the digital models that we have seen so far around the world, they are capable of replicating either the 2D environment, the 3D environment, and even to add some buildings and some 3D representations. However, we have seen in the last years that there is quite a lack of connection of those models with data. So that's why inside the group, we have decided to take this whole level with up to a new level in order to connect it with real-time data and basically make those static 3D models dynamic and prepare them afterwards with integration of all sorts of artificial intelligence algorithms. So we've done that. Before I just show you the demo and conclude, I want to say that digital twin might seem fancy, but if you actually go down to this layering approach, what is happening? You get down to an entire architecture, which require multiple levels of knowledge. So let's start from the bottom. When you start getting data from the sensors or real life actuators, right, or from the physical model, you need to start aggregating, collecting. So all of a sudden, you need to start building databases, either they're structured or unstructured. On top of your databases, you need to start basically cleaning, filtering, fuse whatever data sets you consider they're necessary, and do all sorts of load balancing operations with the data. Only after you did that, you can actually go and start extracting only the features that you need in order to understand your system, select those features, manipulate them, and then basically prepare the terrain for what we call the machine learning models or the optimization algorithms. So either classification of specific products into several classes, either you're trying to predict, well, with a regression approach, the exact values of, let's say, the temperature in production unit and so on. All of that, they are actually consuming what you have already prepared in the past. And what I'm trying to say is that behind all of these steps, there are several technologies that need to be integrated to build a digital twin. So the complexity of this type of system, in order to be able to add this top layer with artificial intelligence, needs to be quite complex. I will wrap up just with this video of the Sydney digital twin model that we have built last year inside the team, basically where we try to integrate not only the spatial layout, the 2D, the 3D layout of the city. This is a replica of all the buildings. But on top of that, we try to add that real-time interconnectivity layer. And what you see here, we have added real-time data from trains moving inside the city. The data is collecting from the global transition feed system, GTFS system, with a high frequency. This allowed us to have like a dynamic model that could be used not only for reaction operations, but only to understand the performance of the entire system inside the city of Sydney. And actually, after we started doing that, we realized, hey, the possibilities are endless, because you can actually interconnect any type of dynamic data that can give you a vision of what is happening into your city. Either we're talking public transport, either we're talking all sorts of sensors for buildings, sensors for water, either we can add the energy consumption, the air pollution, anything that generates data inside the city can be integrated in order to give you that real feeling of what is happening and what decisions can you make. I think one of the powerful things we realized is that you can build scenarios, you can build what if scenarios, and also the big advantage is that once you have this realistic model, you can start testing incident management scenarios. This is just the case that you see here, or along the lines where basically we have a train bunching situation. In this case, the operators could actually see what trains stations they need to address, need to reschedule the timetables and so on. But as I mentioned, what you see currently, this is the water pipe infrastructure with the sensors transmitting data. And I think we have shown as well the air quality data transmission, which provides hourly insights. So there's a lot of work behind this, and the entire team, Yuming, Tu, Merlin, and so on, they have done a fantastic work to integrate all of that, especially when we're looking at this type of level of details. So I think for us, 2022 is basically taking up to the next level of how we can actually use the knowledge that we have together with the integration of prediction models, we have already integrated the train passenger data from mobile, from the Optus mobile operator, in order to predict how many people are entering and exiting the train station, so that in case of disruptions, several actions could be taken. But I will stop here. This is just to give you a demo and showing you what we are currently building and hope to be extended. And then I'll pass on to my special guest from today. And I will start with Professor Jorge Lozoya-Santos. He receives his bachelor in electronic engineering from the Institute Technologico de la Laguna in Mexico, master in automation, PhD degree in mechatronics from the Institute Technologico in Monterrey. I have met Jorge while doing my PhD studies in GIPSA Lab Grenoble, where he was actually working as an active researcher and building the connection between Mexico and France. I think that he has multiple interconnections and joint works with Politecnico de Milano and so on. I will hand over to Jorge for his presentation. After that, we will also hear from his student, Diego Sanabria, with regards to the application of the digital twin modeling that they have done inside the campus. So I will just stop sharing my screen and then I will hand over to Jorge.
Hi, everybody. Thank you for this invitation. Thank you, Adam. Thank you, Simona. It's my pleasure to be here. This is a great opportunity for share our work and also for grow our collaboration. So this is Digital Twins for a Better and Conscious Community. My name is Jorge de Jesus Lozoya-Santos, and I will talk about Tec de Monterrey and what we are doing on digital twins focus on communities. So Tec de Monterrey is a university from Mexico. Let me see if I can show my video panel. If I can hide my video panel, sorry. Okay. We have 26 campuses. It's Mexico wide open university with 3 main campuses: Monterrey, Guadalajara, and Mexico City. So our slogan in research is research that transforms lives. So the facts on research, facts and figures on research is we actually have 800 research faculty, more than or close to 7,000 graduate students. And I would like to emphasize that we work a lot with undergraduate students on research. We have more than 8,000 students working on research. So we are a pretty active university on research from 2015 to 19. We publish more than 5,000 publications, and in average, each of our papers are cited more than 4 times in each year. So, as you know, the collaboration is very important, is the key for the success in research. So the half of our papers that we publish is with international collaboration. And another interesting thing is that 1 paper of 10, more or less, is linked with the industry. So for us, Tec de Monterrey, the link with industry and real problem solving is and the inspiration for doing research. So Monterrey City is a city with more or less 5 million inhabitants in the north of Mexico. So we are the industrial powerhouse of Mexico. Yes, if we want to know what is the Tec de Monterrey in the city, is the red spot I just put right now, is there. Monterrey City is the name of the city is because we are plenty of mountains in the surroundings of the city. And we are located in the north of America, 220, 250 kilometers from the border with USA, specifically with the Texas state. So the Campus Monterrey, as an initiative with the name of Distrito Tech. Distrito Tech is an innovation district initiative. So the innovation districts, they are oriented to develop the research, innovation, and entrepreneurship of this zone in order to boost from this point of the city to the rest of the city, like a wave of innovation and success. So it's a polygon of 452 hectares and includes more than 24 neighborhoods. Some problems in this zone is mainly the people that lives here is gentrified. Okay. So the activation or the problems for the search, innovation, entrepreneurship is very high. So we need to activate this zone with some specific startups and activities in order to get more economy and more active life for interaction between the people. So this is our living lab. Distrito Tech is our living lab. So we are looking to use the Distrito Tech to test about how we can reach a safe, inclusive, and sustainable city. But we are not using only the term smart communities, okay? So we think that the urban spaces can be conscious if the people walking around, living there, they are conscious about how they impact in the surroundings. So we are using the digital transformation tools, the smart cities concept, and the sustainable development goal 11. This SDG is about sustainable cities and communities. The keywords for this SDG is healthy, safe, inclusive, and sustainable cities. So as you can see, the digital transformation technology is about Internet of Things, big data, software, robotics, artificial intelligence. But all of these technologies, the goal is when we use together the intelligence of the systems using this technology will increase according to the complexity of the interactions of the system. So we don't want a city with high technology in the view, but high technology for the communication and the solving of problems. So the main project is the smart communities and conscious communities. And we are using the technology for the increasing of the perception in the community. So how we can use the technology to help the city managers to change the perception of each citizen. So in this figure, the blue squares emphasize the technology as a tool for the typical methods for the evaluation of urban spaces. And we want to impact specifically in the experience of the people. So each icon you can see below the square, they are specific projects for this initiative. So here in Distrito Tech, you can see a layered figure from data to governance. So each layer creates tools for the city, for the people, and how we can impact several things like sustainability, well-being, quality of life, development, and governance. So all the technology is about installations, and the rest of the layers impact in the sustainable goals. So in the rest of this seminar, you will see the Digital Twin for Urban Space project with Diego Mauricio. And we are very happy because we are boosting the interest of our authorities, the all the counselors of the university and also other students to participate in this kind of project. And you can see that we are working very hard in order to link the technology to the sustainable development goals. So here our main challenge today is how we can use this technology to create the digital twin of a corner. If we can understand and instrument a corner in the city, we can show to the managers of the city the value of the technology to take action and to do better things in the urban spaces of the city, specifically in the corner. So the technology is a tool for data generation from urban spaces. The technology is not the each day tool for doing things, but for design better places. The digital transformation technology is a key for smart communities, or mainly conscious communities uses technology in a specific need. So thank you. Thank you, Simona, for this invitation. Now, Diego, it's your turn.
Thank you, Jorge, very much. And it's very interesting to see that you are trying to apply the technology to improve the livelihood of the communities. And I think this should be a major objective. Diego, while you are preparing your sharing screen and presentation, I would like just to give you a short introduction. Currently an undergrad student at Technologico de Monterrey. He is pursuing a bachelor degree in mechatronics engineering and completed his role as a chief engineer in the university's racing Scuderia Tech Racing. He worked as a research engineer intern in the Automotive Consortium for Cyber Physical System Research Group, where he was a project manager and technical lead for the digital twins of urban spaces and the digital cab for Electrobus, a research project. He also has been involved in the BRAIN initiative in Technologico de Monterrey. And I have to say that he will also go this summer to Formula One UK, where he will work as electrical intern. So I'm pleased to pass on to Diego to give us a little bit more tech dive into his work.
Okay, good morning, everyone. Thank you very much for the introduction, Dr. Simona, and of course, thank you for having me. As Dr. Simona mentioned, my name is Diego Botín. I'm currently working and leading the Digital Twins for Urban Spaces project. And well, I'm here to share a little bit of what we're doing, how we're doing it, and what we want to achieve, and of course, what we have achieved throughout the year. This year, 2021, has been a really challenging one for this specific project because it was the year that we started working and exploring this emerging technology of digital twins and discovering all the possibilities that it has, and of course, challenges and limitations that we face throughout the development of such systems. So let me start by giving you an overview of what I will be talking about. Firstly, the project objectives that we have set for ourselves in the development of our digital twins, the methodology and architecture that we follow, and also the results and some systems that we have developed. I would also like to share with you some of the case studies. So how have we used our technology and our development in real case scenarios, real life scenarios, and their actual impact. And well, at the end, close with a conclusion on the subject. So first, talking about our project objectives, Dr. Simona and Dr. Lozoya have talked about the benefits and how digital twins can be used in real life. This technology is used in a variety of domains for a lot of applications. But we are currently focused on the urban space and also on the digital twin of a vehicle. And in this sense, we have one main objective, which is creating a living lab for the analysis of the interactions and the evolution of experimentable digital twins, of course, with a focus of improving our community. So we work under a framework of United Nations Sustainable Development Goals, and we want to prove the value that digital twins have and how can we use it to improve our community. Having said this, we have some specific objectives which relate more to the technical side. So firstly, it's creating virtual models for a vehicle and an urban space based from real input. So using sensors, we can gather information from our environment and produce these virtual models in the most accurate way. We also want to enable connectivity, automatic connectivity between the physical and virtual worlds. And this specific point has proven to be very challenging. And having this opportunity to present to the Data Institute at UTS, I think it's one of the biggest challenges, managing all the information, the really big amount of data that digital twins and sensors can generate is a big challenge that we are currently tackling, but I think it's something that we will continue working on throughout the year. We also need to implement, in this sense, a real-time data acquisition system. And with this, we are using IoT technology and machine learning tools. A little bit about the digital twin state of the art, and this is something that Dr. Simona mentioned earlier, is the maturity spectrum. So this is a spectrum that it was proposed by the Institute of Engineering and Technology, and it's a way to classify digital twin applications nowadays, and it's classified in a 6-level spectrum, where the first level is the least mature or basic implementation of a digital twin, and the final layer is where information is autonomous and of course it flows smoothly and automatically between virtual and physical worlds. I would like to state that these specifically 2 last layers are the most advanced, and there's little evidence of widespread applications of digital twins in these levels, but it's something that it's really possible and what we are working to achieve. In the orange arrow here, I have put it to show that our project currently stands in the first level of maturity. So as of now, after a series of processes with exploration of technology, understanding, research, and system development, we have reached a point where we can generate 2D maps and 3D models of our physical twins, so of the vehicle and the urban space. We are currently working in the second level, where we are connecting our models to the real world with real physical data. And our project is envisioned to reach in the short term, the level 3, where we can enrich our models with real-time information, which will effectively enable the lifecycle monitoring of our physical twins, and in this case, our community. In terms of the methodology, here I have 2 figures. The one on the left is urban space architecture, where as it has been mentioned, there are different layers. Each level adds on to the previous one. But basically, the least mature level would be the terrain. So digitalizing, having a virtual representation of the terrain. And it's basically the geographical information of a space. And the information starts to add up when we have information of the buildings, structures in the area, infrastructure, so how infrastructure and mobility, how the community moves around in that area, how the community interacts with the space. And the 2 final layers, the digital twin and digital layer, well, it's enriching this model with real information. So that's the architecture that we follow. And the other figure is it's divided in the 3 components of a digital twin, which is the physical world, the virtual world, and the connectivity between both. In this sense, our project starts with a physical twin, which is, in this case, a vehicle. Our test vehicle is a Mazda car. The vehicle has been enabled with a real-time data acquisition system mounted on its roof, with some processing units that give us edge computing capabilities. And in this sense, we can take all the information from our environment and move it to the virtual world using some communication interfaces such as Ethernet, USB, a CAN network, I2C, SPI, etc. So our information goes to the virtual world where we have our vehicle model simulation in a way that we can monitor the performance of the vehicle in real time, and our 3D mapping and digitalization module, where we perform the digital twin of the space. Also in the virtual world, we have an IoT data transmission module that we are developing, where we can take the results from the simulations and from the sensors, process it in the most actionable way, and send it wirelessly to an external web server, where an external user can access the information and the historical database. So talking about what we've been working, so the actual development of the project, and I will go through the components themselves. So we start with the physical world, where we have the data acquisition system. And in this diagram, I show the devices that we are currently using. So we have 5 sensors that we are currently using. It's a camera that we use to get video footage from an area. And all of these devices are mounted again in the vehicle. So using the camera, we get footage from the trajectory, from the space, and using machine learning tools, specifically object detection and tracking machine learning tools, we can understand how the people are moving in the area and perform some statistical analysis to find out, for example, pedestrian density in an area, traffic flow, the speed of vehicles moving in a certain area, etc. We also have a CAN bus, so the CAN network in the vehicle itself. We are developing a system that we can use to connect to that CAN network and use the information from the sensors that the vehicle itself already has. Some of the variables that we are interested in measuring are the steering wheel angle, the throttle pedal position, the speed of the vehicle, and some driver commands overall. And these variables are very important to run our virtual vehicle simulation. We also have an IMU, which stands for Inertial Measurement Unit. And this device integrates an accelerometer, a gyroscope, and a magnetometer. So we can read variables like the acceleration and the rotation of the car itself. And we also have a LiDAR, a Velodyne LiDAR, which is a high definition device that we use to take information from the environment, produce a point cloud map, and at the end have a digitalized 3D map of the area. All of these 4 devices send the information to the processing units in the vehicle, which in this case, we're using an NVIDIA Jetson board. It's an edge processor and a computer for the vehicle side of the digital twin. And we finally have a geotab device, which is connected externally that works with REST API communication to have GPS coordinates of the vehicle. So an overview of how we use this information in our project. As I mentioned, we have 2 branches, the urban space digital twin and the vehicle. In this sense, this graph presents the flow of information. So we start with the data acquisition system, as shown in this figure, and we gather information from the LiDAR, the inertial measurement unit, the GPS, and a camera to produce the urban space digitalization. So we use techniques such as a near distribution transform with distinctive feature registration. And this is basically an algorithm to use the LiDAR information to digitalize a space. We developed the trajectory estimation from the inertial measurement unit. We georeference our information with the GPS, And again, with the camera, we can detect certain objects on the road. The end result is a 3D digitalized space. On the vehicle side of things, we use the CAN information and the IMU information to run the vehicle simulator in real time and produce a 3D visualization of the vehicle. And the end result, well, is that we can monitor the vehicle and we can predict some specific variables of its performance. At the end, with our objective, we want to use these two digital twins and create a platform where they can interact. For instance, perform what-if scenario simulations, understanding their inner operations, and having all this information, proposing ways to improve their space, the vehicle, and the way that our community interacts. In terms of the connectivity, as I mentioned, the data acquisition system is mounted on the vehicle. And here, having an inside look to the support, we have the NVIDIA Jets on board, the Velodyne interface box, accelerometer, gyroscope, and the CAN connectivity device. Just to mention that it's important to have this support mounted as close as possible to the center of gravity of the vehicle to eliminate linear accelerations and noise from the vehicle's movement, specifically that might affect the LiDAR and the IMU readings. Moving on to the virtual world. So how do we use the information that we gathered from the environment? For the LiDAR processing algorithm, as I mentioned, we use a near distribution transform with distinctive feature registration. So what this basically means is that we use the LiDAR frames. So a LiDAR takes in a frame, basically like a picture of the environment in the way of a 3D point cloud. And we want to take consecutive frames and stitch them together or merge them together and to have this accumulated point cloud map of an area. So as seen in the figure, this is something that we've been able to do. This is a street from Technologico Monterrey, where we stitch together a series of frames to produce this bigger map. And this is a top view of the 3D map, where we have in the white dots a trajectory estimation of the vehicle, and in blue the whole 3D map, where we can see some structures, the street, some trees in the middle of the street, etc. Now, using this technique, we effectively enable the terrain, the building, and infrastructure levels of our architecture, since we now have digitalized the terrain, the volume, perimeters of our buildings, and we start to understand how the streets and vehicles move inside that urban space. Next up, I would like to talk to, with this algorithm, conclude that through a series of experiments and validation techniques, we have been able to conclude that the system itself has a 98.4% average trajectory distance precision. So when estimating the trajectory of the vehicle, it has a 98.4% precision and a 1.12 average RMSE in the point cloud merging algorithm, which talks about the accuracy of the algorithm that merges subsequent frames. In this sense, these are good numbers. We have a process where we have to balance processing time and precision and accuracy, since if we were to want a 99.9% precision from our system, the processing time would increase a lot. And in this sense, we want a system that can run as efficiently and as fast as possible. And through parameter tuning, we have come to this balance where we have a good precision, good accuracy, and still have a fast processing time. After the information goes from the LiDAR, it's processed into the accumulated point cloud map. And finally, we can display a visualization in the ArcGIS software. And in this ArcGIS software, well, we can see, this is one example. of a street. In this software, we are currently working with better filtering techniques. So in this example, it's the point cloud is prior to filtering, so that's why it looks still a little bit noisy. But it's some of the work that we are currently solving. So using this information, as I mentioned, the LiDAR, the IMU, and the GPS allow us to enable the first 3 layers of our architecture. And next up, we can use the movement of the car and the information from the car, as well as the information captured by the camera, to enable the mobility layer, where we can understand how people interact with the environment and how they move around. Finally, we could use the information from all of those layers, and if we expand our experiment to multiple vehicles using the data acquisition system, we can effectively and continuously enrich the model with real-time information from a space. So this is how our devices impact each layer and how it will eventually enable the digital twin as a whole. In terms of the virtual world, but now moving to the vehicle side, our vehicle model was developed as a parametric model in CarSim, which is a mechanical simulator software. And in this software, we can program the model with different parameters, specifications, to represent in the most accurate way our physical twin, our physical car. Once the model was designed, we moved on to Simulink to enable that model. So in the Simulink environment, which is the figure on the left, we can use the model and run it through various scenarios. For example, we can run it with simulated or pre-designed trajectories, such as acceleration and braking testing, and also pre-designed or logged trajectories from canned data. One of the things that will enable the digital twin is the real-time I/O simulation. So using the variables from the CAN network in the vehicle, such the ones that I mentioned earlier, like the steering wheel angle, the speed, driver commands, etc., we can run the simulation in real time. So using information from the environment or the real physical twin, we can run the virtual world. And this has given us the ability to monitor our vehicle and experiment, compare, and log information from different scenario simulations, and of course have a 3D visualization. Next, our next steps for this development is targeting a predictive performance algorithm, where we want to predict how the vehicle would perform in certain scenarios and how certain relevant components will perform under certain scenarios or conditions. This is another visualization of the CarSim software, where we were able to develop the model of the car, as seen in this image on the corner. And this video shows an acceleration and braking test of our model. So we have some dashboard instrumentation, visualizations, and of course the vehicle itself. And that's just on the side of the vehicle with a simulated pre-designed maneuver. However, as we are moving on to start joining both branches of our project, we designed a digital space in ArcGIS, which, as you might remember, ArcGIS is the software for the urban digital twin. So we designed a space in that software, which is actually a corner from Technologico in Monterrey, and we imported it into CarSim software, where we can test our vehicle, our virtual vehicle, in the virtual digital space. So this is an image of the space where we have the buildings, some trees, and the basic infrastructure model. And these are just some of the first steps on the integration of our two branches. Now, moving on to some case studies. So how have we used our developments to have an impact on our community? Firstly, we have an electrobus initiative here in Technologico Monterrey. This is an initiative that, from Technologico Monterrey and 5 associated companies from our area, from the automotive industry. And it's an effort to create the first electric and connected bus in Latin America, where we want to electrify a passenger bus and integrate it with modern technology to understand the performance and operations of the bus and how it interacts with our community. So the initiative integrates several projects and is based on the Distrito Tech area around the campus, but our specific focus was to develop the digital twin for the bus. In this sense, the CarSim software didn't have the ability or capabilities to do a model for a bus, so we designed our own model. We designed it in Simulink as a physical multi-domain model, so we can understand to a physical level how the bus is performing under various scenarios. The model was designed with a focus of vehicle dynamics. So we want to analyze how the accelerations and forces of the vehicle, the energy usage or waste, and identify some driving styles. So the Simulink interface is the figure here on the left. And on the right, I have a figure of one test that we did. So in this test, we used the electrobus simulator under an acceleration test. So as a step input, we wanted the vehicle to reach 60 kilometers per hour as fast as possible. And we tested the simulator with 3 conditions: when the bus was empty, half full, and completely full. And from empty to full, there's a 5-ton in weight difference. So the performance, of course, is affected. In this sense, we can see in this graph how we were able to see if the vehicle was empty, it reached the reference speed of 60 kilometers per hour a lot faster than if it were completely full. And this is also a behavior that we can see in the braking situation, where the vehicle, if it's empty, it brakes a lot sooner than if it were full. And we were also able to determine the state of charge of the batteries. So in this graph, we can see that the batteries depleted a lot more when it was full than empty. And we can start to see specific patterns that could be expanded to our other driving cycles. Another case study that we worked on is the digital corner one that Dr. Lozoya introduced earlier, where we set out to use our systems in a real application on a corner of Technologico Monterrey main campus. And this is an image of the actual corner that we are focusing on. We chose this corner because, as you can see from the image on the left, the street is a little bit neglected, so it's not in the best state. And we think that in this specific corner, our technology would have the most impact to the community. So this was our experimental setup, where we had our car with the data acquisition system mounted on its roof, again with the devices that I already mentioned. And for the camera, instead of mounting it on the vehicle, we mounted it on a pivot. So this is a robot that is being developed in Technologico Monterrey, and it has cameras on its 4 sides, so we could have a 360-degree view of the corner. And we let it run for about half an hour and gathered results from the corner. Now, talking about the digitalization of the space, this is a video of how the LiDAR merges subsequent frames. This is a sped up video, and it uses all the frames, and again with the NDT technology, it starts merging them, and again in the white line, it shows an estimated trajectory for the vehicle around the corner. And using that result in ArcGIS, we had some visualizations, again prior to appropriate filtering that we are still working on. But this is some of the first visualizations from CarSim, where we want to get to a point where we can have surfaces and, of course, a more cleaner view of the corner. With the other devices, for example, with the IMU, we were able to characterize the state of the street. So analyzing the accelerations and rotations of the vehicle movement, we were able to detect some events in a manual manner, such as a speed bump, a pothole, and acceleration and braking areas in the curve. As I mentioned, this was done manually, but we are currently working on developing the machine learning algorithm to detect these specific events from streaming information from the sensors. And in that way, we can understand the state of the street without being there. On the video on this corner, we have an example of the camera object tracking and detection algorithm, where it detects certain objects such as people, bicycles, cars, traffic lights, etc. And using this information, we can perform statistical analysis to understand, for example, pedestrian and vehicular flow, density, the velocities of the vehicles moving around certain streets. And using all the information from these devices, which is a lot, we have a civil engineering student and an architecture student that evaluated the information and came up with an improvement proposal for the corner.
Diego, I think Adam wants to try to wrap up and go into the questions. So I'll just pass on to you to wrap it off if you can. I think that will be great, so that we can still get questions before people jump into their next meetings.
Yeah,
Thank you.
okay. Thank you, Doctor. So I will move on to the actual proposal, where we wanted to develop a pocket park using the information. We determined some of the most important improvements, like delimiting lanes, pedestrian areas, and making available some green and open public spaces to improve the perception of the citizens and increase sustainability and safety in the area. So just to conclude, some future agenda for us is connecting to the physical world, also integrating all our systems into a single platform and processor, and also sharing with the world all of our findings and developments. So thank you very much.
Thank you, Diego. Thank you so much. I think this was really great. And Adam, I'm passing on to you. We have 2 questions already typed in, but I think for people that are already dialed in, if we want to, how can we get them to speak? Or
Yeah, so easiest way is for people to post directly in the Q&A. If you do want to ask a question verbally, then raise your hand using the icon at the bottom of the screen. We should see that hand go up. I know we're right at the end of our time, so if people do need to leave, no problem at all. And remember, we're recording this so we can share it later. I'd just like to say thank you very much, in particular, to our 3 presenters today. I thought that was just a fantastic session, and in particular, the illustration of the power of digital twins in that last session, Diego, was, I just thought, fantastic. So thank you. All I'm going to do is pass on some questions here from the audience. So Professor Feng Chen asks, there are many DT offerings currently on the market. What are the advantages of those that have been presented today?
Yeah, so we think that the approaches that we used to developing our digital twin focus in a context of Latin American cities where some technologies are not very accessible. So we developed our digital twin in the most cost-effective way, and with a very specific focus on being able to expand our platform to other applications. So, for instance, our methodology, architecture, and data acquisition system for the vehicle can be expanded to other domains such as the urban space, even for human digital twins. And I think this is one of the advantages, the cost reduction and the ability to use it in a number of applications with the same objective of community development.
Thank you very much. And Diego, while we've got you on the line, so Dr. Marian Andre asks, what are the challenges you face when collecting the data from the vehicle, and in particular around the integration of your different data sources? So I know there's a huge amount of data flowing in, and just seeing that LiDAR, my head already explodes in terms of data storage. So what were some of the challenges you faced there?
Yeah, so just something to mention, the LiDAR, for example, for each frame that it takes in around 300,000 data points in each frame. So, and that's just of the LiDAR itself. So I think the biggest challenge that we had was processing and then merging the information. So using different filters and like Kalman filtering, denoising techniques, compression, etc. We were able to merge this data, but I think the management of the huge data set is one of the challenges, and particularly with the vehicle connecting to the CAN network is still a challenge to us, because each car manufacturer has a specific prohibited and hidden IDs and messages on their CAN network. So understanding each signal is a very challenging thing to do with the vehicle itself.
Thank you. We've got another question here from one of our shining stars at the FM lab. So Arthur, he asks, can digital twins be implemented in a horizontal axis? So you spoke about the vertical complexity layers, but both yourself and Simona. So for an example, could it be implemented as one data pool of historical and real-time transport and infrastructure data with an interface? The benefit of that is that it would allow us to build specific visualization front ends and attachable data processing modules. So, and that might include AI. So I guess the question there is, we've got two options, right? We can go further in depth vertically, but also we can go out horizontally. Does that horizontal path make sense for digital twins?
Well, with my particular experiences with this project and the research, the state of the art, I think that digital twins have reached a complex level where, in order, for example, to understand the transportation aspect of a city, how buses or trains move, one has to have information of a lot of layers before that. So the terrain, the different stations, the infrastructure, how people use the transportation system, for example. So I think horizontal development is definitely an option, but one needs to take into account all of the information that goes on beneath that, and understanding the system in a number of layers to accurately model it.
Yeah, I agree with Diego as well. And just to complete on that, in the sense that eventually, even Jorge can complement, you can dump all the data in a data pool, which is great. But what is happening afterwards is that you have specific 3D, let's say, layouts, which are associated only with specific sensors or with specific, how should I say, features of that 3D. Then you have entities which have different features and so on. So eventually, even if you can dump them into the same data pool, but you will still have to regroup them afterwards somehow, because they tell different story, I think. Anyone else? Yeah, sorry.
Oh, no, I was just going to agree with that sentiment as well, Simona. Looking at the time, we should probably wrap up, but before we do so, any questions between the panel members here? So we're talking internationally. It's a nice chance to have a chat. Simona, do you have any questions for Diego or Jorge before we wrap up?
I actually, I would love to see how you have applied the digital twin for the electric bus, and like how this develops this year, because adoption of electric buses, it's also happening in Australia, in Sydney. The entire fleet will be changed to be electric, and they already starting doing that. So I would love to actually, just follow the electric bus initiative and learn from you and what Sydney and Australia can do better to interconnect as well the fleet. I think that would be great. So would love to stay in touch and know more about that one, and of course share with everyone.
Yes,
Yes.
the Electrobus will begin the electrification of the chassis next month. So I think for the end of this year in December, maybe or November, we will have all the Electrobus tested on an urban circuit, ready to go for the service to the community. But the challenge for us is how we can get this trust from the tier one and the bodywork company to take advantage of this opportunity and put sensors and enable new embed and enable new technology to get this information, because they don't know how to do this. So our challenge is to create this knowledge to the industry, and of course for us to sync. This is the sync all this information to a database in real time in order to understand the problems the problems that we can solve, but also as this is only one unit, we need to focus the digital twin only of this unit, because this unit can interact with other ones. Okay.
Thank you.
But sure, we'll let you know, Professor.
Thank you. Thank you so much. I think that's all from my side. Diego, do you have anything else to add before we wrap up?
Just to thank you, Doctor, for the guidance throughout the year. We've been working closely with the development of our project, so thank you for the guidance and support. Thank you for having me, and thank you, Dr. Adam Berry, for the event.
Excellent. Well, I really enjoyed that session, and thank you so much, both Jorge and Diego, for dialing in. And I know it's often difficult to get the times to line up, given that we're on opposite sides of the world. So I really appreciate you making time to come and join us today. It was a great session. Anyone else that's attended today that have lingering questions, feel free to flick them to Simona or I. Very happy to follow up. Otherwise, thank you very much, and we'll see everyone in around a month for the next in our data discovery seminar series. Thank you.
Thank you.
Thank you.